In this video, I'm going to talk about the Fourier transformation that helps determine obtaining the power of spectral density of a simple continuous cosine, which is in both form of the definition of PSD. And so what it helps in simple language is that what the Fourier transformation is transforming the Bloch sphere to a different kind of spectral electromagnetic field containing star, which could be releasing photon or proton. So this is the equation for the Fourier transformation, and phi p equals to 2 pi Hamilton. We put 2 pi Hamilton because this Hamilton is going to be the radius of the Bloch sphere that I'm going to find, and there's the infinite well from positive infinite well to minus infinite well, and we differentiated this value because we want to find the wave function of how the function is going to intercept with the Bloch sphere. And we have E, which is the potential energy. We always put potential energy next to the wave function because the wave function can degrade. And then we put the Hamilton square because we found and we put pi because Hamilton square times pi will be equal to the area of the Bloch sphere. And there's dt, ending the integral. Actually, today in this video, I'm going to solve a question, the delta function bound set. I'm going to solve the delta function bound set, which is this is the problem we're going to solve. Psi x equals to the AE potential energy to the power of minus alpha and absolute value of x. But then the case is that if alpha is bigger than 0, if it is smaller than 0, it's going to be negative psi x, and we can't determine negative psi x because the infinite well is going to be negative. Both of them is negative, then it will become 1. So it's too easy, and everybody knows that. So in problem 1, it's going to be to normalize the wave function and absolute value and normalize the wave function. This is the first step we're going to do. This is kind of a hint on what we're going to do. And then the full purpose is to find the absolute value of alpha. And problem 2, we're going to calculate the momentum space wave function using the Fourier transformation. By using Fourier transformation, we can calculate the momentum space wave function by determining the Bloch sphere and the infinite wells interception. Psi x interception. And Fourier transformation, how do we find Fourier transformation? So this Fourier transformation is found by connecting the position space and the space momentum, which relates back to string theory, which I'm going to talk about in the next lesson. It's a little peek. And then, so since we know that the Fourier transformation equation is this, by knowing this and after I analyze the shape, we'll get to solve these two problems. So analyzing the step. So first of all, you should have this square and infinite well, and since we have a Bloch sphere, we're gonna do this over 1 . I want you all to know that this dt can't be erased because dt is the integral ending formula. So this d over dt is the Noether formula shortened, and the potential energy, we analyze the shape by having the absolute value, put in, and then square the Fourier transformation equation, which gets us this. And we need this to normalize the wave function. Normalizing the wave function is something like this. I'm going to draw the Bloch sphere. This is going to be the Bloch sphere. And then I'll have different pumpkin variation. Like this. It's like a globe. It's like a picture where you see a global something, right? And then this is the Bloch sphere, and this is its center. This is its center. It doesn't look like a center, but it is. And there is the wave function that I'm gonna make, this one. The potential energy will be intercepting in 2 points, this part and this part. We can choose it anywhere, but then it should be connecting the middle. And it can make it intercept here, like this. And this interception will be the y-axis. This will be the x-axis. Like this. And there won't be anything here because this is going to be a multiverse. So this is the Bloch sphere, so we're going to put this as B1 and B2. This one. Analyzing the shape is that this is actually a 3D sphere that intercepts with the y-axis, which is the boundary. And that's why this is called bound set. I did the set theory last time. I did the set theory. The set theory was putting in different values of fermion and boson. And we can actually relate this by having this side as fermion and boson, which makes it easier to solve. But then there's something called complex conjugate that we didn't do. So I'm not going to use that. So first of all, since we know the shape, I analyzed the shape, we know the potential momentum of the Fourier transformation, we know the Fourier transformation basic equation, then means we also know the graph of the wave function. That means we can solve both of them. So number one is normalizing the wave function. This is the wave function, right? So the wave function this is the wave function, right? It's there, but then it says that alpha is bigger than 0, because if it's smaller than 0, it'll be a negative infinite well and become 0. So, I mean 1, so first of all, we're gonna put this in first. We're gonna put this as this, which equals to this. Very basic. And since we know the Hamilton, which is the radius, is that the potential energy, we'll put Hamilton then. If you put Hamilton, infinite well, and this infinite well is going to be x and p. Psi x, which is this, and potential energy is p, right? Minus p, p to the power of minus p, so p to the power of p over 1 times the radius squared by pi. Squared by pi. How we're going to do that is very simple actually. we know that the radius was the potential energy, so E square first. So we're going to put E square here, actually E square, and then minus P, so it's going to be E square pi and dt. We got the basic equation. Now we're going to put the absolute value, and it says to put the absolute value, which is the goal of our problem. So how we're going to do it is we're going to actually do that, and we know that we want to solve this alpha right here. And if we're going to solve that alpha, first gotta normalize it. Right? We're going to do this. You put it at infinite well, x and p, and delta x, right? Delta x. But then AE was the potential energy. E was the potential energy and also the radius. But so the delta is going to be AE minus P. AE minus P, and then psi x comma t. But t was P over 1. But then 1 times the potential energy, which is the radius. So just E. And dt over d. This is the absolute value. This is the answer to, not number 1. This is not the answer to number 1. This is not the answer. This is the normalized version. Now this is the answer. To find the answer, first gotta get rid of this part. And since the method is kind of a shortened version, I think we can simplify it further on. We're going to simplify it. First, we're going to divide it into 2 situations. Plus will be, I won't write anything because it's positive. See, the P that I minus can be divided with d over dt because it's in multiplication. And if we divide it, then it will be AE squared over psi x comma p and dt. This was simple, right? And then we have a minus x and p including wells. But then the minus, see, this one could be minus 1. So we'll take out the minus, put minus here, and x comma p, x comma p, not minus p, a e squared dt. Like this. Divide into 2 situations. Now, how we're going to do this is that e squared was actually, look, e squared actually minus alpha x. If you put complex conjugate, x and p minus a e squared over psi x comma p and dt. We found something. This one has the same value as this one. But this one was this one. That means this doesn't exist and this exists in space. Now if you just put this in and divide it by alpha minus alpha equals to minus e squared, positive e squared x p. We had a negative value here, so if we put in the negative value, it's going to be positive. And this one was complex, the Fourier transformation. Alpha equals to minus e squared. And again, something that's very new is that if we analyze the shape, we got two interception. These two interception is going to meet with this one and disappear. That means this leaves 0. So it's times 1. Alpha equals minus e squared. We got the answer. Yeah, we got the answer. But then we want to know the absolute value of alpha. So we're going to just put in the absolute value. This was minus e squared, so if we put in the absolute value, it's e squared. We got e squared. That's the answer. This is the answer. This is the solution of how it first be analyzed the similarities of three functions, wave function, and while we solve delta function and Fourier transformation function. And then we put in the basic equation of Fourier transformation. We put the values in, got this one. We normalized it. It's a standard value right here. And we want to get rid of this, right? So we divided the condition into two parts, this one and this one. And we knew that this one doesn't exist because this got the same value. And then since we got this, we know that this is this. This part is this. We put it in, right? We get this one to become this, right? This and this is equal to this. So, and then dt. But then this was 0, right? This was 0. So, since this is 0, we got 1, because this is 2 infinite wells, and we get 1, so minus e squared times 1 equals to minus e squared. But the absolute value of alpha is going to be positive e squared. So, we got positive e squared. This was done in the exception that a is larger than 0. Alpha is larger than 0. And if you move on to question number 2, we're going to draw. Number 2 is calculating the momentum space wave function using Fourier transformation. How do we find momentum space wave function? We have the basic wave function here. And this one. This is what we're gonna try to solve. This is the wave function, but we want the momentum space wave function. This is the wave function. We want to have momentum space of this. To find this, we need to use Fourier transformation. That is the only way to calculate that. But we're not just finding the Fourier transformation of the momentum space wave function, we're calculating it. So we're going to draw something. And this is actually similar to what I did in the formula L and T. 2 over L, 2 over L. And we get this almost meeting each other, but in the end they go curved up. Like this. And this area right here is going to be the exact same area. These two are the exact same area, even if they're going in different space heights. We know that this part is almost nothingness, and to find the momentum and wave function there will be almost impossible. Momentum wave function there will be almost impossible. But then I said that these two are going in different space. So finding the momentum space wave function is going to be possible. And if we just put this in, we get this one to become A 2 over L E. This one's going to be A minus 2 over a times minus 2 over L e minus alpha x. We got this. We know that these are going in different space values, and we're going to use Fourier equation now. Now, using the Fourier equation, by using this Fourier equation, we can know different space values easily. And we know that there's no radius between these two because they stretch out to infinity. And if there's no radius, there's nothing to write here. And we want the infinite well, so we have this one and this one. Basically similar to minus infinite and infinite. And then the wave function. And then potential energy. We know that potential energy is the radius, but the radius was LE over 2. So if we times that also by minus p, then minus LEP. Minus LEP over 2 times radius to square, right? Radius is times 4 over LE square pi dt. The thing that's very complex about this is two infinite wells are looking very complex right here. So we want to normalize it, and I think that if we normalize it, it'll become simpler. I think it'll become simpler. Plus minus. First of all, we have to write it down. So what we're going to do is we're going to put this as full. If we put it as row, it'll be much easier. Why I put negative is because this is the positive actually. It's not negative, this is positive. So full row and minus row A. So this is row over E minus alpha x minus, this was rho p, and 4 over LE square pi dt times, it wasn't this, d over dt and dt. We can't get rid of this, as we know, but then we can get simplified. As we did, we just simplified, and we're going to do the same thing that we did here. Square equals, divide this in two conditions. I'm gonna write it a little small. Full E minus alpha x minus full p, and since we have a negative value, this will be actually erased to 0, which leaves dt. This one too. Full minus full E minus alpha absolute value x full p dt. Then we don't want the same it's not the same thing. So this becomes 1, which means it doesn't exist. This exists. So this was the momentum space wave function. We used it by using Fourier transformation. Now we're just going to calculate it. If we calculate this one, which was rho, I mean, this one doesn't exist, right? Minus rho p dt. Yeah. This one is the wave function. Now, calculating this is just calculation, and we're going to just calculate it by doing some complex conjugate, doing this, rho square delta minus rho minus rho p equals to rho square over minus p minus rho delta alpha x. They got pretty simple. Last part, deleting the rows. Rho over, since this is delta is the differentiating value, you'll have just alpha. And since we deleted that, we put rho as this one. Just gotta plug it in back. This will become alpha over alpha x. Got x. And we knew that x was, this was phi, right? This was the radius. This was x. And this one was equal to phi, which was 2.1. Then this equals to 2.1. And then we know that if we calculate the momentum space wave function, it'll be 2.1. In this video, we talked about the Fourier transformation. We got the basic equation of the Fourier transformation. We normalized it. We analyzed how it looks like. And then there was some delta function bound set questions. Number 1 was about normalizing the wave function and finding the absolute value alpha. We did that like this. We got alpha equal to minus e squared, and then we put the absolute value and it became e squared. And then we also calculated the momentum space wave function using the Fourier. We graphed it to understand how it looks like, and then we knew that this is void, so we didn't touch this. But then we knew that this extended in different heights, so we expressed that. We put that in the Fourier transformation. We solved it, got the wave function. We 치환, and we did a lot of calculation. We knew that x equals AE, and this equals 2.1, so x equals 2.1, so the answer was 2.1. We solved two problems about delta function bound set, and this was about Fourier transformation. Thank you for listening.